This problem is concerned with just a square box. It has a pivot point directly in the center, and there are three forces that come against it. F1, F2, and F3. Here it comes at an angle of 45 degrees. And then now we're to calculate the net torque. Remember what torque is? Well, first of all, net torque is simply the addition of all of the torques. So if we can add up all of the torques, that will be the net torque. Let's remind ourselves the convention that torques this way, in the same direction as we in math consider positive angles to be. This is a positive torque direction. This is counterclockwise. Counterclockwise. And let's any force that rotates the object around the pivot point in the clockwise direction is considered negative. So that when we go and add these up, for example, I can tell right now that both of these are forces downwards, but force 1 will be rotating in the counterclockwise direction, so it will contribute to a negative torque, and force 2 will be rotating this object in the counterclockwise direction, so will contribute a positive valued torque. Let's remember the definition of torque. Torque is, we can think of it as a force, a force that causes, remember torque is a twist. It's caused by a force perpendicular to some lever arm. And this distance of the lever arm starts from the pivot point and goes to where the force has its effect. But we also can consider it the effect of a force at some effectively perpendicular lever arm. And I think this second definition will help us, or this second way to view this definition will help us in this problem in particular. So let's consider, from the pivot point, this force has an effective, is working at a lever arm directly from the pivot to where the force is. There's an effective lever arm here, L. And we could break up this force into components and figure out what the force perpendicular to that is. That would be fine. There's a force here parallel. This is parallel to the lever arm, and this component would be perpendicular. And yes, we could then multiply L times force perpendicular and come up with a correct calculation. There's nothing wrong with that. That would be this first form. And that would work. But in this case, I think it might be easier just to consider this force working effectively against a perpendicular lever arm. The perpendicular component of this lever arm L, here's the effectively parallel component of this lever arm. And I think this is actually easier to measure because it's just half the size of this cube, this FL. So I would encourage you to consider torque 1 as equal to F1 times the perpendicular lever arm, which you should know because you know the dimensions of this box. And that is in the clockwise direction. Clockwise direction, which you can represent with a negative sign. And torque 2 will be equal to F2 times a perpendicular component here, perpendicular lever arm, which will be the same, and that will be in, and that will tend to twist this in the counterclockwise direction. So clockwise, that would be a negative value to this one. Counterclockwise, that would be a positive value. And torque 3, well, the effective lever arm, again, is this distance, or the lever arm is that distance, and this force is already perpendicular to that lever arm. This lever arm you can figure out just using some straightforward geometry. We would have F3 times L, and that would be in the counterclockwise direction, so that would have a positive value. Calculate those, add them, and that will be your net torque.